so hi everybody, this is Jason Key at SB Grid in Boston. Thanks for signing on. A couple of announcements before we get started. You can check out our webinar lineup on sbgrid.org. We've got webinars running. Well, we've got them scheduled into September now, but there's a few gaps in there. So if you have speakers in mind who you'd like to hear from, you've got a story you want to tell, let us know. We can see if we can get you onto the schedule. It is my pleasure to welcome Steve Lutka. So Steve is the developer of EMAN2 and is based in Houston at the Baylor College of Medicine. And Steve's going to tell us today about Eman2 and tomography.
All right,
Steve.
Let me get this sharing. There we go. Yeah, I didn't actually update this title slide. Really, what I sort of wound up doing for today is more of a sort of summary of all of the things that changed in the 9.1 release we just put out. So the last time I gave one of these SB Grid talks was about maybe a year and a few months ago. It was a little just before the pandemic started, I think. And I talked about the tomography pipeline then, so I didn't want to completely repeat that. So I'm just going to go over the tomography stuff fairly briefly as part of the sort of introduction. So Eman 2.91 was a long time coming. The biggest thing we were doing sort of was the switch from Python 2 to Python 3, which just took a really long time to get everything working properly. So that's probably the biggest reason why it was delayed. Of course, a lot of developments took place during that time. So there's a bunch of sort of large things that changed and smaller things that changed. I'm going to go through a few of these things in more detail today. So data compression, I'm going to talk about just after this. We now implement data compression throughout the pipelines for both single particle and subtomogram averaging. We've made improvements since the last time I talked about this the subtomogram averaging pipeline. We've improved the resolution and quality and that sort of thing. We're using a new measure, which is based on Paul Penchek's MFSC criteria, which gives very nice local resolution estimates, which have a lot less noise in them, a lot less jumps in them than the old style local FSC that we were computing. And that all of the pipelines as well. We've improved E2 Boxer. There have been lots of complaints over the last maybe decade or so about E2 Boxer and us not having good documentation for it. So we made some internal improvements so it sort of self-documents a little bit better, and you can actually figure out how to use the auto boxing tools in it. This I'm also going to talk about today, the deep learning Gaussian mixture model for single particle variability studies. This is only for single particle analysis right now, but one of the things we're working on is extending this to subtomogram averaging as well. And then there are a bunch of smaller changes, and I'm going to get back to some of these later. We support the EER format if you're using a Falcon 4 camera, which supports very nice compressed images with effectively like 400 frame per second frame rates that you can actually get access to. It's kind of useless at that high a level, but it produces these very nice heavily compressed frames, and you can use those natively now. A bunch of speed improvements. Some of these are related to the data compression, which I'm going to talk about next, but there are other speed improvements as well for reading large numbers of images. We reduced the numbers of times the files had to be opened and closed, and that had a pretty substantial impact on some of the file I/O operations. So overall, there have been some noticeable speed improvements throughout the system, particularly if you're using like a remote file system or something that's slower. And yeah, some of this other stuff I'm going to talk about a little bit later. So let me start with data compression. There have been a couple of other papers out over the last few years about data compression. One came out of the NRAM, and they were actually suggesting using Jpeg compression for archival of images in a long time frame, despite complaints that Jpeg compression isn't really good for scientific data representation. They weren't actually claiming that it was a perfect representation. They were just saying that it allowed them to save something for long periods of time because it was so heavily compressed. And then there was another paper out of Henning Stahlberg's lab, which was talking about this proposed Mrcz file format, which, one of the issues was neither of these papers really looked at how much data compression should be is permitted by the data without losing anything, and still being able to achieve the full resolution of the structure. And we had sort of our own take on how to best handle this sort of from a standards perspective. So this is being written up into a paper right now. We haven't submitted it yet, but we'll put it in bioRxiv and be submitting it probably sometime in the next month or two. Let me start by asking a question. Back to a high school again. If you took a measurement and say it was 16.78325, and then you measured the uncertainty to be plus or minus 0.1, which of these two ways would you represent it in your lab notebook? Clearly, if you did this, you wouldn't get a very good grade in your high school chemistry or physics class. And yet that's really what we're doing pretty much throughout single particle processing right now. We collect our counting mode image frames from the detector, and then they get gain normalized, and they produce these floating point images, which are gigantic, and are obviously have more digits of representation than the underlying data actually contains. So if you think about this from a simple perspective, right? If you're in counting mode and the dose is say 16 electrons per pixels per second, does it really make sense to store that number as a floating point value, even if you've done gain normalization? The largest value you're likely to get out of this is going to be something like, 32 would be very safe, right? So you should be able to represent this with basically 5 bits of data just from that argument alone. But we can make better arguments. If you think about it, the Poisson distribution, which governs counting mode images, so if you're counting discrete events, the Poisson distribution tells you that the standard deviation, the uncertainty of any measurement is basically proportional to the square root of n, right? So if you have 4 counts that you measured, then the error is plus or minus 2. If you have 16 plus or minus 4, 64 plus or minus 8. If we represent that as binary, then we can sort of immediately see that if our maximum number of counts that we need to worry about is say 64, then we really should have basically 1 million, call it, plus or minus 1,000, meaning that we only need 4 binary digits to represent that data all the way up to, which would have a maximum number of values up to 64, maximum value of up to 64. Actually, this is sort of the expectation value. So technically, you're talking about a maximum, which would be even larger. But basically, we're saying that you'd really only need 4 bits to represent that sort of data with the most accuracy that you reasonably would expect. And this is sort of a minimum, the maximum number of bits that would be required to represent the data. If there are other sources of noise in the image, then the uncertainty is larger, and the number of bits that you need to keep is even smaller than that. So basically, our most conservative estimate is that in typical cryo-EM imaging, really 4 bits is all you should keep. The gain correction does throw a few cogs in the works, but actually it's not all that severe. I'm not going to talk about the gain correction issue today, but bottom line is that through statistical averaging, the gain correction problem goes away. So you don't really have to worry about that, even if you're representing these images with a small number of bits. So our approach is basically explicit bit reduction combined with lossless data compression. So we're not using Jpeg. We're explicitly doing a lossy compression by reducing the number of bits, and then we're doing lossless compression on top of that. Now, this example is a really extreme example. So in this case, not only have we limited the number of bits that we're using for storing the raw data, where we've also limited the number of bits to the same number in all of the intermediate representations, the 3D maps, the class averages, everything is basically being represented in a reduced bit representation. Normally, you wouldn't do this because when you're making a class average, your uncertainty is much lower. So you should have more bits in your class average. And that's actually what we do in the system. But I just wanted to sort of show you what this looks like when you take that really aggressive approach. So this is what the canonical EMAN2 tutorial data set, beta-galactosidase, looks like when you don't compress anything at all. This is what it looks like when you do 5-bit compression. That includes the final 3D map all the way across the board. And this is what it looks like when you keep only 3 bits of data. You can see that even the 3-bit representation is a pretty good, darn good representation, even the finer features. Now, there are some funny looking sort of surface artifacts due to the isosurface representation with this discrete representation. That isn't a problem when we're using this in the system normally, because normally we're representing the 3D maps with more bits, even if the raw data is being compressed more heavily. But I'm saying even if we take this extreme case, and how about the FSC curves? If we look at the FSC curves, here are the 3 FSC curves. They're basically indistinguishable from one another. So this demonstrates that at least on that data set, you don't need more than 3 bits. Now, of course, we're going to have complaints if you get really aggressive about your data compression by default. So the defaults in the system are less aggressive than that. The defaults in the system are we use typically 5 or 6 bits for the raw data. We keep 10 bits for the 3D maps. So we keep more bits than we need to make sure that we're not causing any harm. You can get more aggressive if you want to. It's just sort of a question of how you want to balance data storage requirements with the actual project. But even at the default level, there's substantial compression. So the approach we're using, we use HDF5 as the native file format for EMAN2. HDF5 actually natively supports lossless compression. So just using the standard gzip algorithm. Now, you may say, if you read the Mrcz paper, they say, oh, there's this terrific algorithm that we found out in the literature, and there aren't really any good public implementations for it, and we don't think that it's got any intellectual property issues. So we want to implement that for the Mrcz strategy. We've taken the opposite approach. We're going with a standards-based approach, which is even if we don't get quite as good compression. And when I mean not quite as good, we're talking about a difference of maybe, maybe you get 80% compression with gzip, and maybe you'd get 85% compression with this other algorithm. Basically, we're saying that small difference in the amount of compression that you get is not worth the risk of producing data which can't be read 10 or 15 years from now because the algorithm that was used never became a wide standard or something like that. So HDF5, which is absolutely standardized, community driven by a bunch of different fields that use it, natively supports gzip compression. Gzip is also, again, a completely patent unencumbered algorithm, which is used by everyone everywhere, and it's very fast when you don't do heavy compression, and it produces compression that's good enough. On top of that, since the compression is supported natively by the file format, other software like Chimera or IMOD, which can read HDF5, can directly read the EMAN2 HDF files with no changes to their software at all. Although, as I'm going to explain in a second, there is a scaling factor when you do that because we've implemented because of the way we've implemented the bit reduction. So Chimera and IMOD will see these images, which started as floating point images, as integer images after we've done this bit rescaling. And at present they don't know how to sort of do the rescaling to get the original values. But the values that you'd get from Chimera or IMOD are linearly related to the values that you'd have in Eman. So it's basically harmless. You just need to change your isosurface thresholds and stuff. Anyway, so we use that strategy. These are the default levels that we're using right now. You can specify more compression than this if you like in various cases. And the overall impact is, if we look at sort of the original Eman tutorial project, if you go through the whole tutorial and you do some extra runs and stuff like that, using the original strategy uncompressed, that's about 35 gigabyte project. The micrographs alone are about 5 gigabytes. With the default compression strategy, then you get a 10 gigabyte project. So between a factor of 3 and 4 compression, and the micrographs occupy about 900 megabytes. And if you get a little more aggressive and sort of use 5 bits throughout, which, as you saw in my earlier example, would be perfectly safe for pretty much anything you'd want to do, then it goes down to 5 gigabytes, so 7-fold compression. So this is really convenient. You get this benefit automatically through the system at the default level. So basically everything will be smaller and take less disk space. Okay, so that's all I'm going to say about compression. Like I said, that's not published. The paper about it isn't published yet, but Eman 2.1 already is using that strategy by default. I'm not going to say a whole lot about the tomography pipeline, like I said before, because I talked about that at the last time, and it hasn't changed that much since then. I'm going to give you a few highlights, and I'm going to also point you at this short course that we just gave about 3 or 4 weeks ago, I think, at the New York NYSBC, which they recorded. So if you go to this site, you can actually watch the recordings, and that has all of the sort of the theory talks where I gave the detailed talk about the tomography pipeline there. So just briefly, the Eman tomography pipeline now, basically everything is implemented other than the data collection is implemented within EMAN2. So you can use serial EM, or you can use the Thermo Fisher tomography data collection tool, whatever you like for collecting your data. You basically have a raw tilt series. Eman has a very nice process now which deals with the CTF, the tilt series alignment, and 3D reconstruction, all in a single automated step. So you take the tilt series, you feed it into a single program, and it produces a reconstructed tomogram and all of the tilt series alignment parameters automatically. I have fiducials in the little example that you see scrolling here, but it does not require fiducials. It pretty much works with any reasonably well-behaved tilt series, meaning that if the tilt series, if halfway through the tilt series, it shifts by 2/3 of the frame or something like that, then nothing is going to save you there because you don't have sufficient data to really do a good tomographic reconstruction. But as long as the tilt series is reasonably complete data-wise, basically this will work. If you come up with an example case where it doesn't work, just using the default parameters automatically, we encourage you to send it to us, and then we'll try and sort out what's going wrong. We've done this now iteratively with several different labs. We asked Grant Jensen for tilt series which didn't work using his current automated reconstruction strategy. He sent them all to us, and everything works. So that works very nicely. We have the deep learning annotation tool, which we released maybe 4 years ago. This is sort of one of our first real major forays into cellular tomography. And then we have the pipeline now for doing initial model generation from the subtomograms, particle picking from the subtomograms, which you can do either using the annotation tool or a separate deep learning based tool, which is designed specifically for particle picking. And then we have the per particle per tilt refinement. This is a similar overall strategy to what's used for EM clarity and what's used in M. And it can produce reconstructions at comparable resolutions to all of the others, and I'll show you an example in a minute. This is just one representative example of a structure that we've done using this from collaborator Zhao Wang's lab at Baylor. This is the same structure that you see right here. I'm not going to go into the biology today, just in the interest of time. But you can basically see the outer and inner membranes here of E. coli bacteria, and these are transmembrane pumps that actually span both the inner and outer membranes here. So you can see them very nicely here from the side view and very nicely here from the end-on view. So we can box out all those particles. We can reconstitute them into the micrograph, the reconstitution process, to allow you to sort of visualize them in the context of the cell. That was also done with just a single tool in EMAN2. You can then visualize them in Chimera or Eman, whatever you like. We can do nice, reasonable resolution reconstruction. So the best we've gotten to with this particular structure is about 7.5 angstrom resolution. We can begin to resolve alpha helices and that sort of thing pretty well, but that's not too bad for an in situ 3D reconstruction, which was done without fib milling or anything like that. And it's as I said, a double membrane spanning protein. So that was a nice little project, allowed us to get some interesting biological results out of this sort of in situ example. Just very quickly, one other quick little example. This is from one of the standard data sets that everyone uses for testing. This is ADS ribosome, Empire 10064. You can see this is what we got with Eman 2.9. We've actually made a few further little tweaks to make some of the things that were done in M available in Eman 2. Basically, you've got the particles all floating around in your field of view, and we're doing per particle per tilt translational alignments to improve the particle alignment. Well, the improvement here is that it will use clusters of local particles and say that if this particle shifts by a little bit, then the assumption is that nearby particles are probably also shifting by a similar amount. And when you take that into account, you can get slightly improved structures. So you can see this is a little bit better resolved than this. We say 8.5 to 7.5 angstroms. Now, this is where things get a little bit iffy here, right? Because if you look at the paper for Tegunov's paper, he published this EMD 11654 from the exact same data set. And this is the structure he got. And he claimed it was 5.7 angstrom resolution. We're claiming 7.5 angstrom resolution. So clearly there's some issues with how robust resolution estimation is in the subtomogram averaging field in general right now. In single particle analysis, things have become pretty standardized and there aren't nearly as many problems about sort of exaggerated resolutions in single particle analysis, but in subtomogram averaging, it's just only now that people are sort of getting to the resolutions where it really matters. And you'll find there are still some tricky little things that are being done. But in my view, I think our structure is at least as good as this structure. Anyway, you can judge for yourselves. Okay, another topic. I realize I'm sort of jumping from topic to topic here really quickly. I'll spend a little bit more time on this one. This is a brand new thing. It's deposited into Archive, not BioArchive, but Archive, and it's under review now. It's in second round of review with Nature Methods right now. So I'll sort of take you through it a little bit today. This was almost entirely the work of Muyon Chen, who was a graduate student with me and is now a junior faculty looking to get his first grant now. Yeah, so I'm gonna go way back in history here, just as an example to sort of explain how this works. I'm not actually going to take you through the 3D dynamics of this system. I'm going to show you some other examples later, but this is a nice system for sort of explaining how the Gaussian mixture model stuff works. This is a multi-enzyme complex responsible for building hydrocarbon chains in the human body. There are 7 different enzymatic activities present in this complex. This is fatty acid synthase, by the way. 7 different enzymatic activities. We're looking at a particular variant here, which actually is missing the 7th enzymatic activity. But still, basically, you have a substrate which has to visit all of these different sites in this complex. And there was sort of a mystery for a long time in this complex, which is that the distance from here to here is about 80 angstroms. And the substrate sits on the end of an acyl carrier domain here, which is only 20 angstroms long. So how does the substrate get to all of these different enzymatic activities? So this was an example that I've always, I've used over the last decade for the 2D variability analysis in EMAN2. So we look at a bunch of the particles from this data set. These were collected before the resolution revolution that occurred, with the new direct detectors. So you can see they're very noisy particles. Nonetheless, we can make, a nice average top view of this particle. We can overlay that with a low resolution crystal structure that exists. You can see that we've got a reasonable match. And then if we do the old style traditional 2D variability analysis in EMAN2, you'll see a lot of stuff going on here. There's this big rocking motion. The acyl carrier domain in here is bouncing all over the place. There's also a twisting motion like this that you can see if you watch this long enough. There's a whole bunch of motion going on. But this is just 2D analysis, right? This is just letting us see what's happening basically in one view of the particle. And that's not really enough to let us understand what's going on in the system. But we have a problem. We have a really serious problem, which is that the motions that are going on in 3D here, in any given particle image, these are class averages we're looking at here, not individual particles, but in any given class average or any given particle, we only have 2-dimensional information. We don't know where things are in Z in any particular location in space. Now, the same motions that are occurring in this view are also occurring in the other views, but to be able to reconstruct what's going on in 3D, we have to be able to associate a particle in one orientation with a particle in another orientation in the same conformation. And that's a really big problem. And all of the things that you've seen recently with sort of manifold methods for looking at variability analysis are trying to solve that problem. So what we're doing with the Gaussian mixture model is a very specific decomposition of the problem, which allows us to map into sort of a manifold method with a much better intuitive relationship to what's going on in reality. A lot of the manifold methods give you this sort of abstract space and show you there are particles all through it. And they say, then in this part of the space, it kind of looks like this. And in this part, it kind of looks like this. Well, in the representation we're using with these Gaussians in real space, we can actually relate any point in this manifold space that we're going to get to eventually with a specific configuration in 3D space of these Gaussian blobs. Okay, so we can try and represent this multi-enzyme complex with anything ranging from 6 Gaussians to 1,000 Gaussians, right? It just depends on the level of detail we want. But even with 6 Gaussians, we could characterize the overall motion of the system, and that would give us enough information for classification of individual particles. So if we understood the 3-dimensional motion of the system in terms of even these 6 Gaussians, we could then use that to classify the particles and produce higher resolution averages of particles which were in a similar 3D conformation based only on their 2D appearance. So that's where we're sort of trying to get with this whole approach. But basically, you can pick how many Gaussians you want to use in your representation to sort of pick the level of detail at which you want to characterize the variability that's present in the system. So if you use a lot of Gaussians, then you can characterize very fine details in the system, but then you're worried that maybe the data doesn't contain enough information to properly constrain all of them. Or we can use very few Gaussians to represent the system, but then, and we'd have plenty of data to represent it, but then the level of detail that we're getting out in the motion is more limited. Okay, so basically what we're doing here is we have for any given configuration of the Gaussian blobs in space, we can represent a corresponding projection for each particle since we already know the particle's orientation, or at least we preliminarily know the particle's orientation. And then we can compare the particle to the projection and gives ourselves basically an energy function, right? We'd like this to match this as best we can for every particle in every orientation. So that gives us something to minimize, but traditional minimization approaches don't work very well in the system because we don't have, while we have Z information in our model, we don't get any Z information out here. So when we try to if we try to minimize this, we can only do a 2D minimization, not a 3D minimization. So the problem is sparse, and traditional approaches don't work very well for solving that sort of sparse problem. So we turn to deep learning, neural networks. Neural networks are really good at ignoring things that you don't want to consider. So this is a strategy which, if you know anything about neural networks, the strategy is similar conceptually to an autoencoder, but there's some very important differences between them. If you don't know anything about neural networks, the next couple of slides hopefully at least kind of get a little bit of conceptual understanding, but don't worry about it too much. We'll get to sort of some results, and you should at least sort of understand how the results relate to the original data when we get there. But for those of you who know a little bit about deep learning, I figured I'd just sort of quickly go over how things are laid out. So basically, with an autoencoder, there are 2 stages. I'm going to skip ahead a slide and then go back. You have what's called an encoder and what's called a decoder. Basically, you put data into the decoder. So into the encoder. The encoder then reduces the data down to what's called a latent space, which has very few variables. So here you may have 10,000 variables, and then that gets reduced down to say 4 variables here in this intermediate space. And then the encoder and the decoder, so the decoder then inverts the process. It takes this latent space and then tries to turn it back into something that's the same size as what you put in. Okay, this is very similar to something like principal component analysis. The idea is you have something that has a lot of dimensions and you reduce it down to a small number of dimensions. And then you can actually, once you have the small number of dimensions, you can sort of put it back through the matrices to get out the same thing that you put in. Now, in the case of neural networks, this network and this network are trained separately. But the goal is to produce a system which does the same sort of thing as principal component analysis. The big difference is that since it's deep learning, it's nonlinear. So that allows you to do, and it's nonlinear and it's sparse, which means that you can ignore parameters where you don't have very much information. Okay, so the way this is trained, we have a bunch of input particle images. We know the orientations of all the particles. So the first thing we need to do is sort of train the encoder. Yeah, I said encoder and decoder backwards before, sorry. So you train the encoder so it can take the latent variable and produce a configuration of these Gaussians, m times 5. Basically, each Gaussian has an XYZ position, an amplitude, and a width, right? So 5 variables for each Gaussian, and you have m Gaussians. N is the number of latent variables, and that's typically, say, 4. So basically what we're doing here, when we're training just the encoder, is we're setting this to 0, and we're making it so 0 produces kind of the neutral configuration. So it's basically producing this configuration of the Gaussians when you have all zeros in your intermediate vector. If you know any physics, this is kind of related to perturbation theory too. Basically, this is kind of setting the neutral condition for the network. Once we train the network to produce this neutral configuration when we put all zeros in, then we train the decoder part of the network. And when we train the decoder, the input that we use to the decoder is the derivative of each particle image with respect to the Gaussians locations in their neutral configuration. I'm not going to try and say that again. I'm not going to try to explain it in detail, but basically you generate a set of m times 5 parameters, which are partial derivatives generated from each individual image in a known orientation. So you put that as an input in here, and then it goes through the network, and then that produces the output here, which can be turned into a projection, which we can compare to each image, and then we train the network by backpropagation. Okay, again, if you don't know anything about deep learning, the last couple slides probably didn't make a lot of sense, but hopefully at least a handful of you, got at least something out of that explanation. We can also use this strategy to update the orientations of the particles as well, but I'm not going to get into that too much today. Anyway, once we've done that process, what we're left with is we can put particles in. We can put let me go back into the slide. We can put particle derivatives into the network. So for each particle, we can put something into the network, and we can get a latent vector out. This latent vector, we can then reuse the dimensionality further if we like to say 2 dimensions, or we can leave it as a 4-dimensional space, whatever. So we can then do some sort of clustering at it. So this is a 2-dimensional representation of a 4-dimensional manifold latent space that was generated via the neural network. And you can see that it has these sort of clusters in space. Now what I'm showing you is this other standard data set that people use a lot for variability analysis in single particles. It's a depleted 50S ribosomal intermediate, L17 depleted 50S ribosomal intermediate. Basically, it has a whole bunch of different discrete states that are present in the population. So it's a really nice data set to use for classification. So you can see there's some sort of obvious clusters here. If we run a clustering tool on this manifold and then generate structures based on the particles, so each data point that you see here in space, each of these little tiny circles is an individual particle, right? So this populate cluster that you see in space is all of the particles in our data set, regardless of their orientation. So we can then go into this manifold and we can pick any neighborhood that we like, and we can average those particles together to produce a 3D reconstruction, and then we can look at the 3D reconstruction and see what it looks like. We can also go to any point in this manifold, and we can find out, say, at this point, what is the configuration in 3D of the Gaussians that made up this model. So what we did here is we ran clustering, and then we took all of the green particles and we used those to make a 3D reconstruction, all the orange particles to make this 3D reconstruction, and so on. And you can see we get these nice different classes. Just to help visualize this a little bit better, on the same data set, I'm just going to show you this nice little example. So here are 3 similar particles here, which just have smaller changes, then 3 particles here, which have larger changes. And we can sort of see what the different states represent. And you can see how we've characterized the discrete variability that was present in this population. Now, the tool is good for continuous variability as well as discrete variability. But when you have discrete variability, it's really obvious when you get the right answer. So we use this as a nice example. There's one other thing we can show you here, which is what happens if we sort of move continuously across the system. Let me just skip ahead to that. Here we go. So now what we're doing is we're generating reconstructions using only little local neighborhoods around each of these points that's moving across this space. So we're generating one over here, this one is over here, and this one is over here. And this is actually just kind of an interesting effect that as we move across this space and across this space, we observe a similar sort of change. If you look here and if you look here, we observe sort of a similar change as we move in a similar direction through this manifold space. Now, that's not required to happen, but it seems to actually happen fairly frequently when we've done this analysis and other problems. But anyway, this shows you how you can use this tool to sort of explore the variability in your system. I've got one other example, which is sort of continuous variability. So this is the precatalytic spliceosome. Again, this is an Empire data set, so it's nice and publicly available. So there's 327,000 particles, and you can make a nice 7 angstrom resolution reconstruction. So when we apply the dynamics method to this, here's one of the results that we get out. You can see this nice sort of rocky, or rather these 2 different rocking motions that sort of exist within the particle. And I would point out that these are not interpolations between 2 discrete states that we determined from the data. These are each of the structures that you're seeing here, each of the intermediate structures you see here were generated as averages of real particles that were present in the data. So these aren't made up intermediate states. These are actual real states that were observed among the particles in this data set. One of the motions that we observed in this data set was already known and was published in the original paper. One of them actually was not. So we actually found a new mode of motion that's present in the data, which wasn't seen in the original structure. Okay, that's all I've got for the Gaussian mixture model. I hope I didn't go so terribly fast through that people didn't follow it at all, but hopefully you at least got the idea that there's some interesting stuff going on there. So I'm just going to sort of finish up now with a quick demo of a couple of these features that I mentioned earlier on. So first, let's see, this is just a normal single particle reconstruction project here. If I run E2 display, and if you use other single particle reconstruction tools other than Eman, I'd like to point out that there are some very nice just visualization tools that are present in Eman, which are useful even if you do your refinements using Reliant or CryoSpark or something like that. Eman will seamlessly read basically any file format that exists in the cryo-EM field and has this nice browser interface. It'll give you some simple metadata about the individual particles. If I go into one of these folders, for example, I can pick this 3D volume here. If I hit info, I can look at the complete header for the file, regardless of what file format it's in. And then, of course, I've got the variety of visualizations. So this is actually what I wanted to point out, is that now if you open one of these structures that was refined in Eman in the 3D visualization module, you'll see that what you get out is colored. Oops. Actually, let me use a different one. I think that refinement didn't go. Let me try this one. This looked better. Oh, sorry, I got both of them. There we go. So you'll note that the structure comes out colored, where it wouldn't have used to previously. It would have come out looking like that. Okay. Now it comes out colored, and the color that it's showing you is the local resolution map. So if you look at this, blue represents high resolution, and the green here represents lower resolution. So it's basically just a single continuous color scale. If you want to do really nice visualization of this, you have to go to Chimera, and then you can set all the color maps, and you can put a legend on and stuff like that. But this is a nice interface now. So if you go to an Eman refinement and you open a 3D volume and it finds a corresponding resolution volume that was done using this new MFSC that Penchek came up with, then it will automatically load it along with the 3D volume. You can turn it on and off here with the checkbox, and you can also adjust the limits and sort of see. So you can see here that the bluest limit here corresponds to a 0.38 reciprocal angstroms, so something around 2.8 angstrom resolution, and that the lowest resolution color corresponds to 100 angstrom resolution, which is why we're not seeing too much. I can raise the threshold there, and then we'll see it a little more. So it should get all the way to green, sort of. So now we've got 5 angstrom resolution set to green, and the 2.7, 2.8, whatever angstrom resolution set to blue in this map. So that'll load automatically now for you. You can load it manually too if you want. All right. Oh, I lost my presentation. I think it must have gone on a separate screen. Hold on one sec. Let me pull it back up just to remind myself what I was going to show you next. There we go. Right, colored isosurfaces. Oh, E2 boxer. Yeah, I'll bring that up really quickly. Although I'm not sure this project has much in the way of micrographs. Oops. Present in the project. I just want just to show you that we've got the various tabs here for automatic particle picking. And now when you pick each of these tabs, it will tell you sort of what you have to do to use each tab. And there's a little bit more documentation in the individual fields. And I think we actually added one more to this as well. So this will tell you basically a little bit about what you have to do. We improved how well each of these other particle pickers, other than the neural network one. The neural network ones already worked quite nicely. So we improved some of these other ones as well and made one new one available. So just to show that that exists. All right, improved option for XYZ projections. So back to E2 display again. Now I'm in a subtomogram averaging project. One of the issues you'll find in subtomogram averaging, so this project is makes use of some of Beck's nuclear pore complex data. Let me go to this one. So this only uses a very small number, I think 50 particles. Yeah, 50 particles from that large data set. I mean, I think they had several thousand present in the whole data set. So this is just a few as an example. So if I open that 3D file, this is the final average of all of those 50 particles. Obviously, it's not very good resolution, but you know, it looks like a pore. And it has some of the features that you'd expect to see in the nuclear pore complex. Again, this is a resolution map. So again, blue is good resolution, green is low resolution. So the stuff being transported is low resolution instead of high. Anyway, one of the things that you often want to do when you're looking at one of these subtomogram averaging projects is see the individual particles that went into the 3D map. Now, looking at an individual subtomogram of an individual particle is generally pretty noisy. It's often hard to see anything. So very often you'd like to look at these things in terms of projections. So there's a new tool that's available in the graphical interface here, which you can use with one of these particle params JSON files. We have a new strategy which uses LST files for storing parameters. It'll work with those. It'll also work with stacks, with 3D particle stacks, whatever you like. So this file contains the 3D orientations of all of the particles that went into this average. And there's a new button here, which is all XYZ. If I click on that, it'll open a little dialog. It allows me to select a subset of the images. So if I leave it as -1, it'll use all the images in the file. I can also specify a step. So if there are 10,000 images, I maybe want to look at every 1,000th image or every 100th image or something like that. So here maybe I'll say every 5th image, so we only see 10. And then I can pick a sort of a number of layers. So if I leave this as -1, it's basically just going to give me a central section through each 3D volume. If I set, oh, sorry, no, -1 uses the whole thing. Sorry, if I use -1, it'll give me a full projection of the volume in each orthogonal orientation. So it'll give me an X projection, a Y projection, and a Z projection. If I set this to 0, then it'll give me a central slice. If I set it to 1, it'll give me a central slice plus or minus 1 slice on each side added together. So I'm basically making a restricted projection along all 3 axes, and this is very convenient. I can also optionally apply a mask to it. I can include a reference volume. And here, this is important. If I check this checkbox, it'll put them all in the correct orientation, in the orientation that was determined as part of this process. If I don't check that box, it'll show me to them their original orientations from the tomogram. So if I check that checkbox, I say 5 here, okay. It'll take it a second because it has to read all the 3D images and make the projections. Almost, there we go. These are pretty big volumes, right? So these are 320 cube volumes. So it takes a little time to generate them. And what we're seeing is XYZ slices altogether. I think I left that at like 1 or something. So it's actually pretty hard to see anything here. Let me do that again. If it takes a second. Yeah, let's set that to something like 20. So that'll give us 41 slices summed in each direction. So it's still kind of central, but it includes enough density that you'll be able to really actually see something there. Sorry, we'll have to wait a second for that to get computed again. Obviously, if the volumes are smaller, this goes a lot faster. Okay, and now we can see orthogonal views. Oops, sorry, that didn't work. Oops, there we go. So in this middle view, you can see we're sort of looking like this, but we're looking only at a slice through the middle, so we can sort of see the membranes, the inner membrane curving around to the outer membrane here, inner membrane to the outer membrane. So this is a single individual particle from an actual cell of the nuclear pore complex. You can't really see much of the protein density here until you've done the average. And what you'll see here is that some of these, like this one, what's going on here? You've got the parallel membrane coming in here, but now this one's kind of all the way up here. It's kind of funny. This one looks kind of okay. This one looks kind of okay, but you can get a feel for what's kind of going on in your data set. How about this one, right? Where in this orthogonal view, you can see the double membranes coming in this side, but you don't see anything here. This is actually a case where the tomogram was cut off by the fib milling process, so that the top of the pore was actually fib milled away. So we actually only had kind of one side of the channel. Anyway, so this gives you a quick tool for actually looking at individual particles when you're doing subtomogram averaging. A similar button also exists for individual 3D models, so you can quickly make these restricted XYZ projections and visualize them. So you can see, obviously, it looks a lot nicer when you do it in the whole 3D structure. That's sort of a nice additional tool that really targets the tomography audience. The last thing I wanted to show just really quickly, this is for more sort of advanced users, is we're trying to integrate a little bit more with Jupyter Labs now and Jupyter Notebooks. There's now a tool. If I run E2 display -- server, it will open this little window here. And now I'm going to go here and I'm going to type e3.py. You can tell we're moving towards Eman2. Oops. Oh, sorry. And what it's going to do is basically launch a Jupyter Lab session. All right, so there's the web browser showing the Jupyter Lab session. I guess this is probably fine. So we can just execute a little bit of this. I can make some test images. And there's this command now, E3 display, which is available in the Jupyter Lab session. And so here I've made some 2D test images here. And here I can display one of those test images one of those stacks of test images. And you can see that a window appeared here. And it contains the 4 test images that I made here in a list. So I made 4 test images in a list. And then I ran E3 display. And what I see here is sort of a screenshot of what I get over here. If I do this again, now that I've resized the window, you'll see I'll get a window that's actually the correct size. But over here, now I have this image MX test 1, which matches image MX, which was the name of the window, I guess, which matches test 1 here. So this is an image MX display, and the image it's displaying is test 1. The name of the display is test 1, and I can call display again, and I can change the contents of this, or if I want, I could say call. Let's see, try this. Let's see what this does. Oh, I haven't made the data yet. So this is going to make a 3D plot. And now you can see this opens another display here in E2 display. And here it's an interactive display, just like in Eman normally. And here you get a sort of a screenshot of what you see. And if you want to update the screenshot, you can call this again manually. So it's not fully interactive at this point. You can't do interactive manipulations here, but it opens it in a window over here where you can work with it interactively, and you can do all the normal things that you could do with any of the Eman widgets, open control panels, save files, that sort of thing. But it still gives you a snapshot in the notebook for sort of archival purposes and that sort of thing. So this is now available in the system, and we're still improving this and that sort of thing. But that's kind of a peek at the future. Okay, that's basically it. Yeah, future stuff, I've already told you a little bit about that stuff. We're really aggressively working at some new things for EMAN2. We've got some whole new refinement strategies, some of which are based on that Gaussian mixture model stuff I was just talking to you about. So we're really kind of revamping the way we're doing a lot of the refinement stuff internally. We're working on extending the Gaussian mixture model with subtomogram averaging. We've got more deep learning stuff going on and more GPU usage, all sorts of stuff going on for the next major release. But you know, everything's a work in progress. Just acknowledgements. Of course, I got to thank the grants that have continued to support Eman over the years. These are not all of the people that have worked on Eman, but these are the people who have sort of recently contributed to all of the stuff that I was talking about today. And with that, if we've got a few minutes left, I'll take some questions. I went a little longer than expected.
I'm going to allow people to unmute themselves here. So you can ask questions directly. You can also send questions to me by chat if you'd like, and you can hit the reactions button. You can raise your hand like this. It will bump you up to the top of the list, so I know you have a question, and I can call on you. So there were a few. I know I could kick it off, just some basic stuff with the data compression. You talked about disk space savings. What are you seeing in terms of like computational time savings? So do you save time computationally when you are on the
definitely. When you make it a fifth the size, then it can load the file 5 times faster. I mean, the processor is massively faster than the hard drive, so the cost of the data decompression is negligible. When you're writing to disk, the compression costs a little bit, but we're using mode 1 in the data compression, so there's barely any cost there. It has made an improvement. Anything that's disk intensive.
Reduced memory requirements?
No. Once it loads into memory, it's using the uncompressed or full floating point representation.
Okay. Yep. Got a question here. Let's see. It's kind of a long one. Let's see. Is the GMM for SPT coming with EMAN3? Estimate release date for EMAN3?
If I give an estimate for Eman2, it'll probably be about as accurate as it was for the 2.9 release, which was delayed like 9 months from when I thought we were going to do it. We try to do 1.5 releases a year normally. Eman3 may be a pretty major overhaul, so I'm guessing realistically probably sort of the end of the year, early next year, something like that. Of course, we have all the intermediate releases and stuff like that, but I don't think we're going to do another release in the EMAN2 series. You'll note that it went from 2.3 to 2.9, sort of indicating that that the current release is like a preview of a lot of some of the stuff that we're going to be putting into 3. Yeah, it's my best guess. The GMM applied to tomography. It's kind of working now. I'm told. I haven't played with it myself yet. Muyuan's been working on it really heavily recently. I'm guessing probably over the next 2 or 3 months we may have that in sort of a form where it's fit to be used. Right now, if you download a snapshot version instead of the stable release, you could probably play with it, but I probably wouldn't with the GMM stuff yet. It's really not there yet. I mean, for tomography, for single particle, we're also improving it for single particle, but there was something that was at least usable in the release for single particle.
So on the GMM note, we had a question from Jeffrey Willard. So you can go ahead and unmute. Go ahead.
Okay, thanks for the great talk. I really appreciate the GMM paper. I've given it more than one read, and I'm wondering what do you think is the kind of bottlenecks for that and working on those things that is going to allow more high resolution features to be sort of kept intact over different dynamics? Is it mainly the capacity of the model, having it, more complex model, more Gaussians, not spherical Gaussians, or is it mainly like something deeper rather than just compute and more the whole?
So, all right, I think there's a confusion there. This is common. Actually, in the first review round, one of the reviewers raised a similar sort of question. So the version of the paper that's being reviewed now is actually almost twice as long if you look at sort of the methods as the version we first posted to bioRxiv, or so to archive. Sorry. There's a big difference between the Gaussian representation and the resolution that you can get, right? So the number of Gaussians that you're using is sort of limiting the level of detail at which you can represent the motions, right? Basically, so say you had a single alpha helix which was waving around in space or something like that. If you generated your Gaussians at 20 angstrom resolution, then you probably just wouldn't have a Gaussian which was occupying that feature in a way that you could resolve it. But anytime, most of the motions that you see in macromolecules are much larger scale sorts of things. As long as you can characterize the motion, which doesn't take very many Gaussians, when you do the reconstructions, you're using the original particles, right? So the limit in the resolution that you get is basically how big an area, if you're looking at one of these embedded spaces here, am I reconstructing using this, or am I reconstructing using this, right? If I use the points just from here, and I have enough of them, I can still get to a very high resolution, ostensibly in the structure.
Okay, yeah, it's going back to the original
but I have
data,
to have enough
so
particles for that very local neighborhood to be to get to that resolution, right?
Okay, thanks.
Yeah.
So I had a related question, so I'll just jump in here since you've got the slide up. The thing that jumped out at me with these is that there are, if you think about these as sort of conformational landscapes, because these white areas are huge barriers, right? These are, and some conformations have low barriers, like between the purple and the one above it. It can sort of jump between them. Have you looked at sort of what, like if you see this sort of top, it's got sort of a little land bridge that connects it to the next one, like, what those conformational, those interchange points almost, right? Like,
I understand what you're saying. So this particular system isn't a great system for considering those issues to an extent, because what you're looking at here is really discrete variability, right? We're having basically a ligand is present or a ligand is absent. It's not waving motions in space and that sort of thing. Now, within one of these local blobs, you will see some local motions which are probably also involved in the function of the structure, but the big barriers that you see here are basically ligand binding events. So they're things that shouldn't be continuous. They should be discrete. You have to be a little careful also when you're looking at these 2D spaces. So the energy space that we deconvolved the data into here was actually a 4-dimensional space. And then when you used additional dimensional dimensional reduction methods to bring it down to 2 dimensions. So the dimensional reduction method does funny nonlinear things often as well. In fact, I think this one was nonlinear. So the fact that you see a big barrier here, it may not have been the same if you looked at the actual 4-dimensional space. So you have to be a little careful about that sort of stuff as well. But in principle, yes. I mean, the idea that this could be treated as sort of an energy space, and you can look at the population, where the populations of the particles are, to sort of trace actual real paths through the particle dynamics. That still works here, just like it does in all the other manifold methods. But that's more for continuous variabilities.
Yeah. Question from Pete Meyer.
Thanks. This is another follow-up question about the Gaussian mixture models, and it's very likely a naive question.
It's okay.
But in principle, what would be stopping things from just having one Gaussian for each atom in the protein, and assuming you had infinite compute power and you could sort out the optimization problems, just do the reconstruction that way?
That's not a naive question. That's actually sort of an obvious idea to try, right? What begins to become a limiting factor is the noise level of the particles. So at the moment, there's a really hard limiting factor, which is the GPUs that we have right now can't handle models that are that big. So the space, the dimensionality of the deep learning here, right? So we have an m/5 input vector here and a few layers here, and then another m/5 here. So if you have, say, 100,000 Gaussians or something like that, then these matrices become too big, and the memory is the GPU memory isn't capable of holding it, and it would be so computationally intensive right now, it just wouldn't be tenable. So once you reach a certain scale, we can't do it because we don't have the hardware to be able to do it yet. But beyond that, there are the fundamental questions of whether there's enough signal present in the data to do it on a per particle basis or not. But you're thinking in exactly the direction that we're going with some of the new refinement strategies. You don't need to take it to that level to be able to use it as a tool for getting more accurate particle orientations and refining other parameters. So you could do that with even, say 1,000 Gaussian. Oh, I mean, you can do it with 6, but you can do it pretty well with even, say, 1,000 Gaussians. So then you can simultaneously characterize the orientations and the variability of the particles in a model like this. There's some really interesting things that we're beginning to be able to do with that, but none of it's quite ready for discussion at this point in time. Beyond the fact that it's an obvious
like
direction.
A very elegant way of handling, like, how do you handle conformational variability and heterogeneity? Like, this looks like a great way to do it.
Yeah. So for small particles, you could actually begin to do that now. For small, like less than 100 kD, you could actually generate enough Gaussians, and the particles themselves are small enough that you actually can kind of fit it into the GPU memory. But if with the scaling being n cubed, it gets bad pretty quickly. So we're 5 years down the road, then maybe we'll have mega GPUs with a terabyte of memory, which can handle that sort of thing easily. But there are definitely limits now.
Yeah, and I'm wondering, like, I know that a lot of the tech companies have been pretty big into the deep learning space, and that they generally have enormous data sets where they have different training algorithms, and I'm not up to speed enough on any of them to know if those would fit. But yeah, I think if we wait for them to come up with better GPUs and manufacture enough that we can buy them, then maybe we can find out.
Yeah, it'd be nice if they made more, wouldn't it?
Everybody's supply chains have been scrambled by the events of the world these days.
Yep, it's a problem. Hopefully it'll go away in the next year or so.
Hopefully. Thank you.
Steve, before we wrap up here, would you mind sharing the NCCAT course link again?
Oh, sure.
Maybe
if you just go to the NCCAT website, it's really easy to. Where was it? Oh, sorry, it was the beginning there.
Yep.
Yeah, there.
All right.
Yeah. If you go to the NCCAT website, it's really easy if you go to activities, but there it is.
Great. Yeah, we did one more request for the link. So
okay.
All right, great. Well, if there aren't any other questions, thank you very much, Steve. This is fantastic. Always impressed by how much EMAN2 and soon to be EMAN3 can do. It's a very impressive piece of software. 2.91 is out, it's available, and we'll keep our eye out for EMAN3 in the next year or so.
Thanks for the invitation.
Yep. Thank you. Bye. And thank you everybody for joining.
Bye.
Take care.